Welcome back to online classes, Water Chemistry Part 4 under Module 4. Today's topic for discussion is estimation of fluoride in a water sample. So fluoride has some disadvantages if it is consumed. For example, if the concentration of fluoride is more than 1.5 ppm in a drinking water, when we consume such type of water continuously, then it will cause a dental fluorosis. So same fluoride content around 1500 ppm, it is used in a manufacturing of the toothpaste to take care of our teeth, that is to avoid the decay of your teeth. This is a external thing, it is not consuming. So around 1500 ppm of fluoride, it is added in a toothpaste to take care of our teeth from the decay process. If that concentration goes beyond 1500, again it will affect the teeth. So that is called as dental fluorosis. So in drinking water, the concentration of the fluoride should be less than 1.5 ppm. So if the concentration of fluoride is greater than 1.5 ppm and such water daily if you are consuming, and if the concentration goes beyond that, then it will affect our skeletal system. So and it reacts with the calcium of the bones to form a calcium fluoride. So this problem we call it as a skeletal fluorosis. So higher concentration of consumption of fluoride in a drinking water causes skeletal fluorosis. That means the bones becomes very weak in nature. So the permissible limit of fluoride in a drinking water is 1.5 ppm. If it is beyond this, and then it will cause a skeletal fluorosis, weakness in the bone density, bone strength decreases. That is why it is necessary to study how much of fluoride is present in a drinking water. And also I mentioned, so in a toothpaste around 1500 ppm of this fluoride is added, that is called as dental caries. That means it will take care of the teeth. If this concentration is more than 1500 ppm, again it will cause a yellow color to the teeth, and enamel of the teeth becomes weak in nature. So hence we need to study uh, the concentration of water sample. For that, the method that we follow is called as a spectroscopic method. It is also called as SPADNS method. Here SPADNS stands for the name of a reagent. So the name of the reagent used here is sodium 2-para-sulfophenyl azo 1,8-hydroxy 3,6-naphthalene disulfonate. This is the expansion of SPADNS. For our experiment, we are not using SPADNS alone. So we will be using ZR-SPADNS in the acidic medium. Acidic ZR-SPADNS will be used. So the principle of the experiment goes like this. So the fluoride reacts with the zirconium alizarin red lake, dissociating a portion of it into a colorless anion, hexafluorozirconium 2- ion. The bleaching action of the reagent is directly proportional to the concentration of fluoride ion. The meaning of this is, so look at this picture. So all these are acidified ZR-SPADNS reagents. How exactly it is prepared means, so SPADNS is a separate reagent, ZrOCl2 zirconyl chloride is a separate reagent. These two are mixed in a specific quantity and concentrated HCl is added to this. SPADNS reagent 1, zirconyl chloride reagent 2. When these two are added with a known quantity of concentrated HCl, that is called as acidified ZR-SPADNS. So this acidified ZR-SPADNS, it will be red in color. I'll repeat again. It will be red in color. Hence we call this as a reddest lake. So ZR-SPADNS, it is red in color. So only it is called as zirconium alizarin reddest lake. It is red in color. You can see here. You can see here all these are ZR-SPADNS reagents. In the acidic medium, it gives a red color. To this, a different concentration of fluoride will be added. 0.5 ppm, 1 ppm, 1.5 ppm, 2 ppm, 2.5 ppm, 3.0 ppm. So like this, a different concentrations of fluoride is added. When the fluoride is mixed with this, so the fluoride ion present in the solution bleaches the color of the ZR-SPADNS. So ZR-SPADNS in the acidic medium, it is red in color. So now what happens is, so when it is mixed with a fluoride solution, a non-concentration fluoride solution is added to ZR-SPADNS red color. So this fluoride ion will bring about the bleaching of the reagent. So during this process, a new compound, a colorless substance will be formed, that is zirconium hexafluoride anion. Zirconium hexafluoride anion, it is a colorless substance, no color to that. It is a colorless substance. Let me write down. This is colorless. At the same time, proportionate to the amount of fluoride added, the bleaching takes place. That is why the SPADNS becomes free and it is orange or yellow in color. So that's what we can see in the picture given at the right hand side of the slide here. See, as the fluoride ion is bleaching the reagent, it is producing a other color, a yellow color or orange color solution. The intensity of these solutions will increase with increase in the concentration of the fluoride present here. That means higher the concentration of the fluoride added to the reagent, higher would be the bleaching action. Therefore, the intensity of the SPADNS reagent released will also increase. The color of that also will increase. Lesser the concentration of the fluoride added to the zirconyl solution, less is the bleaching action. That is why the amount of SPADNS released will be less, and that is light yellow color in nature. So by measuring the color intensities of these solution after the bleaching at a 590 nanometer, it is possible to quantify the fluoride ion present in a solution. This is the principle of fluoride estimation. So I'll give the summary of the principle. So initially, individual reagents SPADNS and zirconyl chloride are mixed in a specific quantity. A known quantity of concentrated HCl is added so that it becomes red color solution. So that is taken in a different flask like this. Later, to each of this, a known concentration of fluoride solution will be added, like 0.5, 1.0, 1.5 ppm, 2 ppm, 3 ppm, like that. Depending on the strength or a concentration of the fluoride ion present, so the bleaching of the reagent takes place. The red color will be start bleaching. So due to this, SPADNS will be released. So depending on the amount of SPADNS released in the solution, it will impart a yellow color. So higher the release of the SPADNS, higher would be the yellow color intensity. Lesser the SPADNS release, less is the yellow color, like this. So it will give an increasing color intensity to this flask with increase in the concentration of the fluoride ion. So by measuring the color intensity of this solution at 570 nanometer against the same ZR-SPADNS blank, it is possible to quantify the fluoride ion present in a solution. This is the principle of the experiment. Now, moving on to the procedure. How exactly we do the experiment? For that, we need a standard called as uh, sodium fluoride standard solution. So, that is prepared by weighing 0.221 gram of sodium fluoride. So, this is 0.221 gram of NaF, sodium fluoride, is dissolved in 1000 cm cube of the distilled water or a millipore water. So this is the distilled water. When you prepare like this, it is called as 1000 ppm sodium 1000 ppm fluoride solution. The strength of the fluoride ions in this is 1000 ppm. So I'll repeat, 0.221 gram of sodium fluoride. It is dissolved in 100 ml of the distilled water or a millipore water to give a 1000 ppm fluoride solution. This is called original stock. From this, further dilutions are done. How the further dilutions are done means, so a known volume of this is taken. So for example, we take a 10 ml of the above solution. We take a 10 ml of the above solution and made up to or made up to 100 ml, say made up to 100 ml, taking 10 ml of the original stock, and we are making up to 100 ml using a distilled water. How do you calculate the concentration of this means? So we can have N1V1 formula here. N1 into V1 is equal to N2 into V2, N2 into V2. What is this N1 V2 concept means? So I wanted to prepare a 10 ppm solution, say. So here I wanted to prepare a 10 ppm solution, say. So I'll put the strength as a 10 ppm and the required volume for me is a 100 ml. So I'm putting this as a 100. I'm putting this as a 100. Or I wanted to prepare 100 ml, 100 ppm, say, then I will take it as a 100 here. So my needed concentration is 100. So I will take it as a 100 strength, 100 ppm. Multiply that by V2, the volume in which standard flask you are going to prepare means 100 ml standard flask. But what is my original stock? My original stock is 1000 ppm. How much quantity I need to take means that is V1. V1 is equal to divided by the original standard of the fluoride solution. If I simplify, you can see, so it is 10 ml in, see, 2 zeros cancel, again 1 0 cancel. So I have to pipette out just a 10 ml of the original standard. That's why I told, so 10 ml 10 ml of the original stock solution is transferred into 100 ml standard flask. I mean to say this is our 100 ml standard flask. So this is our 100 ml standard flask. Working standard, I am taking a 10 ml. This is 1000 ppm solution 10 ml and make it up to the mark using distilled water. So make it up to the mark using the distilled water. When you do like this, the concentration of this we have mentioned here. It will give you a 100 ppm solution. 100 ppm solution. This is called as preparation of the working standard. So let me give the summary, students. So in the exam, no need to write, but you should know. While writing your answer, the concept should be clear. So original stock solution is 0.221 gram of NaF. It is dissolved in 100 ml of millipore or distilled water. It will give us 100,000 ppm fluoride solution. Now, this is further diluted to obtain a working standard. For that, the simple formula we make use is N1V1 is equal to N2V2. Right hand side, what is the quantity and ppm you need? I wanted to prepare 100 ppm. So, in place of N2, I have taken 100. So, in which standard flask? 100 ml standard flask. So, I have substituted the 100. Which quantity of 1000 ppm I can use? So that is why V1 is equal to this much. When you simplify, it is giving you the 10 ml. So only in a 100 ml standard flask, when you take 10 ml of the 1000 ppm diluted up to the mark mixed well for uniform concentration. This will give us a 100 ppm solution. But here the standards are 0.5, 1, 1.5, or in our experiment let us take it as 1, 2, 3, 4. How to get the further dilution means same simple formula you can make use. So that means I wanted to prepare a 1 ppm solution, say. So same formula, NV is equal to NV. Right hand side, what you have to prepare? Left hand side, what do you have? So now I wanted to prepare a 1 ppm solution. I wanted to have a standard as a 1 ppm. Let n is equal to 1. Which is the standard flask you will be using? So I am going to use a 100 ml standard flask. So I'll put it as a 100. What quantity of working standard I need to take? So V is equal to divided by N. My working standard is 100 ppm solution. So my working standard is 100 ppm solution. So if I do like this, so but here I have taken a 50 cm cube. 50 cm cube means it will become a 0.25 only. So 100 get cancelled and V becomes 1 ml. So 1 ml if I am making up to 100, then it is called as a 1 ppm solution. 2 ml making up to 100, so then it is giving you the 2 ppm. 1.5 ml making up to 100, it will give you the 1.5 ppm, something like this. So hope you understood the first part, how the working standard, original standard, all the standard solutions are prepared. So now this 10 ppm solution is transferred into different standard flasks. So like 1 ml, 2 ml, 3 ml, 4 ml and 5 ml is transferred into 100 cm cube standard flask. It is not 50, it should be 100. 100 cm cube standard flask. This is the step 1. So now we want the bleaching should be done by only the fluoride ion. By chance, the test sample is going to have a chloride that will also bring about this bleaching action. We want to avoid the interference of the chloride ion. Hence, to all these solution, 1 drop of sodium arsenate will be added to avoid the problem of the chlorine. So 1 drop of sodium arsenate is added. If you add sodium arsenate, what happens? The chloride ion binds with the sodium to become a sodium chloride. Hence, it will not bring about this bleaching action. After that, so the coloring reagent is ZrSPADNS. Acidified ZrSPADNS. So we have to add to all the flasks. First, we need to take a only fluoride solution. Blank means don't take the fluoride. So 0.5 means I told it is 5 ml, make it up to 100. So then it is 1 ppm means sorry 0.5 ml, make it up to 100. So 1 ppm means 1 ml. So 1.5 ppm means it is 1.5 ml. 2 ppm means 2 ml. So 2.5 ppm means 2.5 ml, like that. But for our experiment, let us take it as 1, 2, 3, 4, 5. That means ranging from 1 ppm to 5 ppm will be our standard. So 1 ppm, 2 ppm, 3 ppm, 4 ppm, 5 ppm means 1 ml, 2 ml, 3 ml, 4 ml, 5 ml of 10 ppm solution will be transferred. And blank means no addition of the working standard. No fluoride solution is taken here. After that, what we do? We add what is called as sodium arsenate to all. After that only, we are going to add this zirconium solution. See, zirconium solution, that is ZrSPADNS solution will be added. So this is the blank. Now this is 1 ppm solution, 2 ppm solution, 3 ppm, 4 ppm, 5 ppm, like that. Proportionate to the amount of the fluoride present in this, the bleaching will take place. So resulting in opposite color, a yellow color solution. The intensity of these yellow color solutions will increase with increase in the concentration of the fluoride ion. Because see here, according to this reaction, when ZrSPADNS and fluoride are mixed together, the fluoride will bleach this and all the fluoride ions will bind with the zirconium and SPADNS becomes free. So that is what the yellow color formation here. Higher the fluoride concentration, higher is the intensity of the yellow color developed. Lesser the fluoride ion concentration, lesser is the yellow color solution developed here. So this yellow color will absorb the light radiations at 570 nanometer. We can measure the intensity of this. So this will give you the calibration curve like our colorimetry. So known concentration, known absorbance will produce a calibration. For example, take this as a sample. Sample, we don't know the concentration. The same procedure should be followed. 10 ml of the sample to that one drop of sodium arsenate followed by 10 ml of acidified ZR-SPADNS reagent. When you add like that, again the bleaching will happen here. So proportionate to how much of fluoride is present. For this also, using this as a blank, we can measure the absorbance. From the calibration curve, we will come to know the concentration of the fluoride ion present. So now x-axis we need to take 1, 2, 3, 4, 5 F minus fluoride concentration. Y-axis is the absorbance corresponding to that. 1 ppm, the absorbance is 0.02 say. 2 ppm 0.04 say. 3 ppm 0.06. Like that, known concentration, known absorbance, and for the blank absorbance and concentration is 0, draw a line passing through the origin. This is called as a calibration curve. For our unknown, the absorbance, we will get it from the spectrophotometer. From there, draw a line and drop the perpendicular. The point of touching the x-axis will tell that much of fluoride is present in whatever is the volume of the water sample taken. That's how we can determine the fluoride concentration in a water sample. So, water sample, the limit of fluoride is less than 1.5 ppm. If it is exceeding, then it will give a problem to the human body. Hence, it should be taken care. Moving on to the subtopic, that is ion exchange or demineralization process of softening of hard water. In the earlier classes, we understood what is the meaning of hardness, hard water, etc. See, the hardness or a hard water means water which does not produce lather with the soap solution easily. We call it as a hard water. So water, it is not going to give a lather as soon as you apply or mix with the soap. It will not produce a lather. Such type of water, we call it as a hard water. See, this hard water we can't use in the boilers. So you know the limit for the boiler feed water less than 2 ppm. Also you know the ions responsible for this one. So the ions responsible for the hardness, in the earlier classes we have discussed both anions and cations are responsible, like calcium ions Ca2 plus, the cations like calcium Ca2 plus and Mg2 plus. These are the cations. And which are the anions responsible for the hardness means it can be the bicarbonates, but bicarbonates can be easily removed. How? Just by boiling. So it can be removed. Whereas the other two ions like Cl minus chloride ion and sulfate ion SO42 minus, it can't be removed by the normal boiling method. That time we should go for other technique like permitted process, chemical treatment or ion exchange method. One such method only is demineralization of hard water by ion exchange method. So that means under boiler feed water I mentioned, all the boilers will be also equipped with the ion exchanger. What is the role of these ion exchanger means it will remove the ions causing the hardness, both cations and anions. The ions which causes the hardness can be eliminated completely by the use of these ion exchanger. So now let us see what are the parts of the ion exchanger means. It consists of two columns. See, the first column is called as cation exchange column. The second column is called as a anion exchange column. I'll repeat again. So ion exchanger is consisting of two columns. The column 1 is called as cation exchange column. The column 2 is called as anion exchange column. Here you can see. So these resins which are filled in this, see, these are called as a resins. You can see the picture here. These are the resins, cation exchange resin and anion exchange resin. The column 1 is filled with the cation exchange resin and column 2 is filled with the anion exchange resin. So what is the difference between these two means? So the cation exchange resin is nothing but a long chain insoluble cross-linked organic polymer, but it will have a functional group like SO3H as well as COOH. I'll repeat again. The cation exchange resin means it's nothing but a long chain insoluble cross-linked organic polymer, but possessing a specific functional group like SO3H and CO2H, a carboxylic acid group and sulfonic acid group. That means it's a long chain compound. So here the R means it is a cross-linked polymer and the functional group is simply represented by the H plus. So that means the H plus will be replaced with the cations like Ca2 plus and Mg2 plus during the process. Hence we represent the cation exchange resin as RH plus. Similarly, what is this anion exchange resin made of? Again, it is a long chain insoluble cross-linked organic polymer only, but it will have a functional group as OH hydroxyl group, a formaldehyde group or NH2 group. A general functional groups present in the anion exchange resin are NH2, formaldehyde or OH minus. That is why simply we represent the anion exchange resin as R-OH minus, cation exchange resin as R plus R plus, where R is a cross-linked polymer, H plus is the functional group. So these are the resins. Now coming to the working, how exactly it is going to work. So this is the hard water. The hard water filled, initially it is supplied into the first column. It is run through the first column. The first column, the functional group present is a RH plus. Whole thing it is represented as a RH plus. Imagine this water is having the high hardness because of Ca2 plus and magnesium 2 plus. So the hard water has the cations like Ca2 plus and Mg2 plus. The resin is RH plus. What this our RH plus does? So the H plus of the RH plus will exchange with the Mg2 plus and magnesium ions. In the previous slide I will show you. See, this is what we have in the resin. That means the resin has RH plus. The water is run through the first column. The hard water has Ca2 plus. These H plus are replaced or exchanged with the Ca2 plus. Hence, so the water is free from the calcium ions. Similarly, if it is Mg2 plus, Mg2 plus will be taken up by our resin. The water is free from the Mg2 plus. So the water which is running out from the first column, in the first column, whatever water coming out, it is free from the Ca2 plus ions, Mg2 plus ions. How it is? So here RH plus, when the water is running through the column, H plus is replaced with the Ca2 plus. H plus is replaced with the Mg2 plus. So like that it is a continuous process and water will be free from the H plus. Now this water, the water which is coming out from this is completely free from Ca2 plus and Mg2 plus. With the help of a compressor, it is pumped into the second column. The second column is filled with the anion exchange resin. That means it is capable of exchanging the anions. What are the anions causing the hardness? It is Cl minus ion, SO2 minus ions. So the water now do not have the cations like calcium and magnesium. This is not there. This is not there. All these are trapped by our resin. Now, once it is fed into the anion exchange resin, so these ions are getting exchanged with the OH minus of the resin. We will show in the previous slide. The cation exchange resin normally, the anion exchange resin normally represented by R-OH minus ion. Now the feed water is having the sulfate ion, or feed water will have the chloride ion. So this OH minus is exchanging with the sulfate, OH minus will be exchanging with the chloride ion. Hence the water will be free from OH minus. H plus OH minus, it is nothing but the H2O. So the water is completely free from the anions causing the hardness. So that's how it is possible to soften the hard water. How long it will be functioning? So now the water which is coming out from this is completely free from both cations like calcium and magnesium, anions like Cl minus and SO4 2 minus. So it is free. It will be functioning continuously at one stage. All the H plus of the cation exchange resin and OH minus of the anion exchange resin will get exhausted. No more H plus, no more OH minus in the second column to exchange with the ions which are moving, are coming in. So that time it is necessary to regenerate the columns, make it working, regenerate the column. So how we will come to know that it is exhausted with the H plus and OH minus ions? So the water which is coming out here will be tested. So if it is hardness is very high, implies that the columns are not functioning. That time it is necessary to regenerate. How do you regenerate? Now this is saturated with all the cations like calcium and magnesium. Our resin will be saturated with Ca2 plus and Mg2 plus and no H plus will be there. Everything is used up by the hard water, and here similarly here all the OH minus are used up and we will be left with Cl minus, SO4 minus on the resin. On the resin surface we are going to have these ions. So how to regenerate means, now to remove these, to remove the calcium and magnesium ions, to remove the calcium and magnesium, the column number 1, that is cation exchange bed, is cleaned with the dilute HCl. It is cleaned with the dilute HCl. Now the resin is saturated with Ca2 plus, Mg2 plus. We have to clean this with the dilute HCl. That time what happens? See here, the column is saturated with the Ca2 plus or Mg2 plus. When you are running the acid for some time, all these Ca2 plus or Mg2 plus getting exchanged with the H plus of the HCl to get the resin will come back to the original status, that is RH plus. This is called regeneration of the column 1, and this will go along with the wastewater to the drain. So very hard water go to the drain. Similarly, how do you clean your anion exchange resin means? So now the anion exchange bed is saturated with Cl minus, SO4 2 minus with the R group. We wanted to have a OH minus ion, hence NaOH solution is injected. So NaOH solution is injected into this, continuously washing with the NaOH. So the Na plus ion will take away this Cl minus, SO4 minus, the resin will come back to the original status, that is ROH minus. You can see here. So this is the column 2. Column 2 is saturated with either SO4 2 minus or Cl minus ion when you are running or cleaning with the alkali. So this SO4 2 minus or Cl minus ions are getting exchanged with the OH minus ion. The SO4 2 minus and Cl minus goes to the drain and your resins are regenerated, ready to use. So that's how the regeneration of the columns can be done. So that's about the ion exchanger. So this all the boilers will be equipped with this type of ion exchanger. Raw water directly cannot be feed into the boilers. Otherwise, you know what are the problems it will cause to the boiler in the later stage. So what is the advantages and disadvantages of the technique? The advantages of the ion exchange technique is, so it is that the ion exchanger can be fitted with both the types of the boilers. One is a high pressure boiler, the other one is a low pressure boiler. And also it is easy to convert or soften all types of water like highly acidic water, highly alkaline water, everything can be treated properly and we get a hard water having a hardness less than 2 ppm. This is the advantage. Coming to the drawback, so installation cost is little bit high. Once it is installed, the functioning will be easier. And if this water sample is having the ions other than calcium and magnesium, that cannot be removed. For example, the metal ions present are Fe2 plus, Mn2 plus, something like that. So then it cannot be exchanged with the resin. So it is impossible to remove these type of metal ions from the water. So resins are not suited for these type of impurities. Coming to the last one. So as much as possible, the water which we are running through the ion exchanger should be transparent and clear. If it is turbid, the resin gets saturated or resin becomes inactive in nature, it will get clogged. So that means The water, as they clog the resin, these turbidity, the colloidal particle will present on the surface of the resin, and it is not readily available. The H plus ions of this or OH minus ions of this is not readily available to react with the incoming water. Hence, it cannot be. We cannot supply the turbid water for purification in the ion exchanger. These are the disadvantages of the ion exchange method. Otherwise, it is a very good technique. So that's all for today's class, students. Left out thing we will discuss in the other class. Thank you all.